It's a real pleasure to be here, first time in Mumbai, and I've been having a great time, so thank you. And I must say also, one of the things I really like about India, I never ever see so much discussion in seminars, and it's really wonderful. I wish we could import this back home. Okay, so what I'm going to be discussing is, it's a set of techniques, and these techniques, the common thing about them is they all use the symmetric group. So the set of permutations of n objects. We understand this group very well, so I'm going to be using what we know about this group to solve certain problems in physics. So let me tell you first of all a little bit about the background of what we were trying to do when we started on this process. I think it's remarkable what progress has been made in n is equal to 4 super Young-Mills. Integrability has been discovered in the planar limit, and I think before this was discovered, maybe people didn't believe that this was possible. However, I also think that the planar limit is a very, very small piece of the theory. So what do you do in the planar limit? You are focusing on operators with a dimension delta, and you have to restrict yourself so that delta squared over n is very, very much less than 1. So what kind of things do you leave out when you make this restriction? Well, one of the things that you leave out would be operators whose dimension is of order n. And this would include things like, for example, giant gravitons. And what is a giant graviton? This is just a spherical D3 brane. So this is one of the things that you would leave out that you cannot treat in the planar limit. Another thing would be operators that have a dimension of order n squared. In this case, the operator is actually heavy enough in the dual gravity, that is, will back react. It will produce a new spacetime. And in particular, if you wanted to write down an operator that would be, say, dual to a black hole, you would expect you have to write something down with a dimension of order n squared. So by restricting to the planar limit, there's a lot of interesting questions that I think you don't really have access to. Now, in the usual planar limit, we understand a lot. Yep.
So any kind of n dependence of delta
Yep.
would violate the planar expansion. So even square root of n and
Yeah.
things like that.
Okay.
Isn't it? I mean,
Well, if you have, so let's put it like this. So this has been asked. So the kinds of questions that were asked is, so one of the things that you're used to from the large n limit is factorization. So if you have some product of gauge invariant observables, the expectation value of the product at large n is the product of the expectation values. So what you could ask yourself is, if I let delta grow, at what point do I start to violate factorization? So certainly if I hold delta fixed at order 1, I have factorization. But in fact, if I have delta scaling like n to the alpha, and I can take alpha less than less than 1/2, I still have factorization. So in this case, in fact, what's happening? As you increase delta, the number of fields in each operator is increasing, so the number of Wick contractions is exploding. But it has to explode fast enough to overpower 1 over n squared. If alpha is less than 1/2, although you've got a lot of diagrams that are non-planar contributing, not enough of them to overcome the 1 over n squared. When do you start to overcome the 1 over n squared? When delta is order square root n.
Nice. So that is to say that the next term in this series, which
Yep.
is 1 over n, I presume?
So usually, if you were working planar, this term would have been an order 1 over n squared. You would go to,
Okay.
yeah, the torus.
All right. So, but if I allow delta to have some independence, then
Yep.
the usual topological expansion will not be there.
Absolutely.
Because it's some other strange power.
Absolutely. Absolutely. So in fact, so these are the kinds of questions we wanted to answer. What replaces the topological expansion when you're talking about these heavy operators? Is there something? Is there some analog of factorization? So we would still expect the large n limit of the theory to simplify, but how do you see that? So this is the class of questions that motivated us. Okay. Good. So in these lectures, what I'm going to try to do is I'm going to tell you what the basic strategy is, and then I'm going to try to build it up in a series of examples. So I'm going to start off by talking about, first of all, counting and constructing gauge invariant operators in n is equal to 4 superyoung-moles. Then I'll talk about calculating their correlation functions in the free theory. Then I'll talk about calculating their correlation functions at weak coupling. And for example, when you start to study operators dual to giant gravitons, you really see from the n is equal to 4 superyoung-moles the open string excitations emerging and the brane world volume emerging. In much the same way that in the planar limit you really saw the closed string emerge, here you can see branes plus open strings emerge. So I'll try to convince you that you can. And then I will talk about a slightly different application, but using exactly the same methods, which is essentially to count and construct primaries in free CFTs. So for example, if I tell you I've built the primary from n fields, I tell you the dimension of the two spins of the primary, you might want to know how many primaries are there with this set of quantum numbers, and secondly, how do I construct them? What's an explicit formula for this primary operator in terms of the basic fields and some sprinkling of derivatives? And I'll show you that that can also be boiled down actually to a question about the symmetric group, but we'll get there. Okay. I am not going to be very good with giving references, but there is one acknowledgement that I'd like to make. All of this work has been done with a very good friend and colleague, Sanjay Ramgoolam. So it's been 15 years now, I guess, that we've been collaborating together. So I owe him actually a big intellectual debt, and I just wanted to acknowledge that. Okay. Now let me tell you the basic strategy, and I'm going to try to illustrate it in the simplest possible case, and then slowly build up to more and more complicated examples. So in the first examples, I'll do everything explicitly, and then afterwards I'll rely on the simple examples for some of the details. So here's the basic strategy. So I've broken it into 3 steps. So in the first step, it's possible to enumerate certain objects that you want to study, whether these are gauge invariant operators, primaries, whatever. So you enumerate by sprinkling indices on an object. So that's the idea. So we're going to put some integer on this object, and then to get different objects, we shift these integers around. But shifting the integers around can be viewed as some permutation. So here I'm really enumerating by permutations. Once you've solved that problem of enumerating, there's an interesting structure that you see. And the structure that appears is that the enumeration is redundant. So not every permutation will correspond to a distinct object. This redundancy it's a signal of some symmetry. And it's a symmetry of some structure that you have in the problem. And it's actually very basic structure, because all you're doing is labeling these objects. But then what I'm going to show you is, surprisingly, it's possible to exploit the symmetry and learn something novel. So that's going to be the basic strategy, and I'm going to try to show it to you working again and again in examples of slightly increasing complexity. So the first example that I want to look at is gauge invariant operators. Gauge invariant operators in the half BPS sector of n is equal to 4 superyoung-moles. So what are we doing? You know there are 6 adjoint scalars that are Hermitian. We combine 2 of them to produce a complex combination. So we've got Z, which is phi 1 plus I phi 2. Under the gauge symmetry, we know what would happen. Z would go into U dagger Z U. So if I ask you what is the full set of gauge invariants, you'll tell me take products of Z and take traces. So products of traces. So that's what the full set of gauge invariants are. So for example, okay, so what I'm going to do, first of all, two indices. I'm going to denote the Zij row column, put the indices in different places, the two transform differently. And then, for example, if I take n is equal to 3, I can consider something like trace Z cubed, which would just be, let me say, I1, Z, I2, Z, I3, I3. And this would just, of course, be trace Z cubed. I can also look at, say, trace Z squared, trace Z. This would be Z, I1, I2, Z, I2, I1,
Yes,
Z.
it's confusing.
Sorry? Yes?
So the first one doesn't look like trace Z.
Sorry.
Yes.
Very good. That was a little test for the audience. Great. Good. Now, what's the difference between these two guys? The difference between these two guys is, take a look at how the lower indices are organized. So I've got a 1, 2, 3. Here I've got a 2, 1, 3. So all that's happened is I've swapped the order of the 1 and the 2. Okay? So in general, I could write Z, I1, Z, I2, Z, I3, I sigma of 1, I sigma of 2, I sigma of 3. Then if I want trace of Z cubed, what permutation should I take? Identity. If I want trace of Z squared, trace of Z, what permutation should I take? Swap 1, 2. But there's two others. What else could I use? Swap 2, 3, 1 and 3. Absolutely. So here, in fact, is an example where we're getting a redundancy in the description, in the enumeration. And we can also look at trace of Z cubed. And here you can see that sigma is equal to 1, 2, 3 will do it, or 1, 3, 2. So fine, we enumerated these bottom indices. I chose n is equal to 3. And there we go. There's a redundancy. Now you can see that what's going on here is that this redundancy is...
What is 1, 2, 3? That's cyclically moving, right?
Exactly. So 1 goes to 2, 2 goes to 3, 3 goes to 1, and yeah.
So in this example,
Yeah.
1, 2, 3 and 1, 3, 2, of course, correspond to the same operator.
Absolutely.
Right?
Absolutely.
And just like in the other example, 1, 2, 2, 3, 1, 3, they're all of this operator.
Exactly. So what you can see is we have enumerated the primaries. You give me a permutation sigma. Sorry, we've enumerated the gauge invariants. You give me a primary sigma. I'll give you an operator, but it's certainly not unique. And what we're seeing is permutations that belong to the same conjugacy class give the same gauge invariant operator. Okay, so now we've got the redundancy. We've got the symmetry. Okay, by the way, why is this a symmetry? Well, I can think about this as a trace of sigma Z tensor 3. So that's the notation that I'm going to use. And what I'm imagining here is Z tensor 3. Sometimes I will write capital indices, ij, so this is just notation. This is Z I1, J1, Z I2, J2, the usual thing that you would think, I3, J3. And the permutation I'm going to realize in this space as ij would be delta I sigma of 1, J1 delta I sigma of 2, J2 delta I sigma of 3, J3. And if I multiply these two things together and take the trace, I'm getting exactly that expression sitting over there. Okay? And we'll build the structure a little bit more just now. So the next thing that I want to do, we've enumerated, we've got a symmetry. I would now like to exploit this symmetry. And we're going to exploit this symmetry by doing a Fourier transform.
Sorry,
Yep.
can we, I'm sure it's obvious, but can we see why operators that are related by conjugation give the same gauge invariant operator?
Sure. So the reason for it is the following. If I take, so the Z's are bosons.
So it's related to the fact that the Z's are identical, right?
Exactly. So if I take Z tensor 3, and I act with gamma inverse, where gamma is defined like this, I'm just swapping the z's around. So this is the same as z tensor 3. Nothing happens. Plug that in there. Sigma is the same as conjugate to sigma. Okay, so in actual fact, this symmetry is Bose symmetry. Yeah?
And the cycle structure is giving you the number of traces.
Exactly. So the cycle structure, so this is so this I would say, I could also write it like this. And there you see the 3 z's. I could have put in the 1 cycle. See, I give you the cycle structure. The 3 cycles then give you the trace z cubed. Absolutely.
And how are you seeing trace identities from this point of view?
No trace identities yet. Well, we will get them. Now, what I would like to do is I'd like to exploit this symmetry to learn something novel. And what I'm going to do is I'm going to use the Fourier transform. Now, so let me just say something. Maybe this is obvious to you, but let me just remind you in that case about how to think about the Fourier transform.
Just before that, I mean, the Schur polynomial basis that I have encountered
Yep.
in while studying this algorithm thing. So, in which way are they like some superior kind of basis compared to these?
Sure, absolutely. In fact, in 10 minutes, we'll have the Schurs. And I'll try to say why they're superior. And if I didn't succeed in answering that, please ask me again.
Because they take into account the trace identities.
Exactly. Right. They take account of the trace identities. Yep. Okay. So now, so let's just talk about the Fourier transform. And the Fourier transform will appear a lot. So we'll be using Fourier transforms on double cosets and various other spaces. So let's just talk about what the basic idea is and why are we calling this a Fourier transform. So we've got the redundancy. I now want to exploit it. So let's look at the usual Fourier transform. So the usual Fourier transform is related to the group of translations. And you know the group law. If I translate by B and then by A, that's of course the same as translating by A plus B. So we have here an abelian group. So that means all irreps are one-dimensional. So all irreducible representations of this group are 1D. And that also means the group element is equal to the character and so on. If we take the usual Fourier transform, so f of k equals integral dx e to the I kx f of x, maybe tilde, minus infinity to infinity, I want you to think about this as follows. So if we look at e to the I kx, this of course gives us a representation of this law. E to the I ka times e to the I kb is e to the I ka plus b. Here, k labels the irreducible representation. So every k is a different irreducible representation. The a here, now here because it's an abelian group, every conjugacy class just has a single element. So sometimes when I talk about a group element, I'll have to tell you, think about it as a conjugacy class or an element. Here you should think about this as a conjugacy class label. And then what we're doing over here, you can see that this is a transformation from something defined on conjugacy classes to something defined on the irreducible representations. And it's given by taking a sum over all elements of the group, the character, so this is the character, and your function. So that's what we want to do now in various other cases, finite groups, double cosets, things like that. So for our case sitting over here, we know what the characters of the group are. So the irreducible representations of Sn are labeled by a Young diagram of n boxes. So this means the Young diagram has n boxes. This R here is a label for irreps. Sigma is defined on the conjugacy classes. So all permutations of the same conjugacy class gives me the same character. So this object is the natural analog of e to the I kx. So now what we're going to do is we're going to change from a function that was defined on the conjugacy classes to something that's defined on the irreducible representations. So chi r of z is equal to 1 over n factorial sum over sigma is an element of Sn, chi r of sigma trace of sigma z tensor n. And this is the Schur polynomial. So it's just, if you like, a Fourier transform from the trace basis. Now, why is the Schur polynomial a nicer set of gauge invariant operators than the traces? And the reason essentially comes because of so-called trace relations. So we're interested in studying operators, perhaps with a dimension of order n or order n squared. And in that case, you have to be careful about the fact that not all traces are independent. So as a very simple example,
Sorry, and
yep.
R is a representation of the permutation of the n elements where
Exactly.
you have trace Z, where you have ZA, NZ.
Absolutely. Yep. So what you can see here, if we have a Young diagram, for example, with 4 boxes, we would be talking about S4, and there would be a total of 4 fields in the operator. So there would be 1 box for each field.
And representations of the shamefully ignorance, but representations of the permutation group of
Yep.
S4 are labeled by Young diagrams.
Absolutely. Yep.
The same Young diagrams that for SU4. So you can't have 4.
Exactly. Yep.
It's just
So
the cycles, the size of the cycles, right?
Precisely. So, right.
Sorry, that symbol I didn't get. What is
Oh.
R perpendicular?
Okay, good. So this symbol R perpendicular n, translated into English, is R is a partition of n. And the reason why we think about that as a Young diagram, imagine that you have got this. I could think about this as 3 boxes, 2 boxes, 1 box. So that's a partition of 6.
Number of rows.
Exactly. A number of boxes in each row. Exactly. That would give us the partition.
I see.
Yeah, yeah.
Yeah,
Okay. So let's imagine that I have a 2 by 2 matrix. So let's maybe set Z equal to lambda 1, 0, 0, lambda 2. So a diagonal 2 by 2 matrix. Something that you can check very easily is that the trace of Z cubed minus 3 times by the trace of Z, the trace of Z squared, plus 2 times by the trace of Z cubed, if you just plug that in, vanishes. So if you were going to write down a set of gauge invariant operators just given by trace of sigma Z tensor 3, and you were studying 2 by 2 matrices, you would already make a mistake if you listed these 3 operators as independent. But now you need somehow, how do you look at this complete set of gauge invariant operators and select from that set those operators that are independent? How would you do that? Yes? Yes.
When you have the identity permutation, sorry, not the identity, but the cyclic permutation, the cycle of the largest length, what is the decomposition in terms of the Schur polynomials?
Okay, good.
Is it just the strip?
No. So you mean if you take, for example, something like trace, I don't know, Z to the 5.
Yes.
Okay. So what this would be, so this particular case has been worked out. If you give me an arbitrary cycle structure, my honest answer is I don't know, because we don't know the characters well enough. This one has been worked out for any n. And the rule is you take the first one, 1, 2, 3, 4, 5. So that's everything in one row of Z. And now add a sign and cycle 1 box along. And then it comes back to plus and cycle 2 boxes along. And keep going until you've got a single column. These are called the hooks. They look like a hook. And in fact, trace Z to the n is a sum only over hooks with an alternating sign.
You know, if there were just 2 boxes, this is the special case that we all know trace of two boxes is trace z square plus trace z, the whole thing squared by 2.
Exactly. Yep.
Sorry, one more question.
Yep.
This quantity here
Yes.
looks a little bit, now suppose I think of Z as an SUN matrix.
Good.
This thing looks a little bit like the character in the representation R
It absolutely is in SUN.
in SUN.
Absolutely.
Okay.
So and in fact, I want to talk about that connection.
Okay.
Yep.
What is the counting of trace relations? How do they grow with the...
Okay, good. So I don't think that that's completely understood, even for a single matrix. What happens is, as soon as you've got Young diagrams that have more than n rows, they are set to 0. Now, if you have operators of dimension order n, hardly any Young diagrams have more than n rows. Once you get to n squared, order n squared boxes, the edge of the diagram gets some typical shape that was described by Ketov. So you've got some typical shape for the edge of the Young diagram, and in this case, when it's order n squared, the trace relations really will remove some significant number of states. So that's when it becomes important. If you ask exactly how many states are removed, maybe there is a result in math that I just don't understand, but as far as I can see, we don't really have a good idea as to exactly how many are removed. And when you go beyond one matrix, which you'd like to do, then it becomes much more difficult, but you can still write down the trace relations, and we'll see what they are. Yeah.
But you know, for one matrix, you can just do the counting, right?
Absolutely.
You can count, ignoring trace relations, and you count
Yep.
with trace relations,
And take
then
it.
you can subtract.
So
For one matrix, I think you could get an answer.
in fact, so at this level, we can do any number of matrices, just scalar matrices. I'll show you how. So we know how to do the counting with finite n and the counting with n infinite.
Right. But generally, with many matrices, it's a matrix model, right?
That, exactly.
You know, which you
So-
can't in general solve.
Okay, so the counting of that matrix model, I'll show you, I'll map it into another problem. Yeah. Okay.
Just
Yep.
one more thing. So this is the Schur polynomial combination you were saying.
Very good.
Now that's the same as the one that comes from the Cayley-Hamilton theorem. I mean.
Yes, exactly.
Annihilative polynomial.
Absolutely.
You have to explain that. What is
So-
Cayley-Hamilton theorem?
It so basically there is this. Maybe he can.
So if you take, if you look at the det of z minus lambda 1, say, times the identity, that would have to vanish. Okay? Now, what this det is, this would be completely antisymmetric. And in fact, you can check that this guy, you're saying nothing but that Schur polynomial vanishes. And this is a determinant, which is how it gets related to that. Okay? So in actual fact, when you want to take into account these trace relations, okay, so these are called trace relations, written in terms of the sigma variable, it would be very hard to somehow extract from this list just trace C sigma tensor n. If n is less than n or equal, no problem, everything survives. But as soon as n is bigger than, little n is bigger than capital N, it becomes difficult to know which ones do you keep. In the Schur polynomial language, it's very easy. Only keep Schur polynomials for which R has at most n rows. That's the rule. Now this is really a bit of a shock when it comes out. So, so trace relations accounted for by saying R has less than or equal to n rows. And now you should be quite surprised, because all that we've been talking about is how we were swapping fields, and all of a sudden we're saying something about the size of the matrix. How did swapping fields suddenly know about the size of the matrix? This is a completely different thing. We haven't put that in at all. So I want to explain to you why the two get related. This is something called Schur-Weil duality, and I just want to show it to you working in a very simple context. So we already saw, so let's say Zij acts on some n-dimensional vector space V. Then a tensor product of n copies will act on V tensor n. Now let's put a basis for V tensor n.
So just
Yep.
to understand this condition, so even when this small n is larger than n, the cutoff naturally is not small n but capital N.
Exactly. Yep. So it's a bit weird, right, that the symmetric group knows about capital N. Why? So if we want a basis for V tensor n, what we can do is pick a vector, ei1, for the first vector space, tensor that with a vector for the second vector space, and keep going until you've included a basis vector for the last vector space. Let these run over a basis for each of their respective V's, and now you have a basis for V tensor n. Is that clear, what the basis is? Now what I want to do is, I want to define two actions on this. So the first action I've got is Sn. So what will Sn do? So for example, let's imagine that we take 1, 2, and we apply it to this basis vector. All it will do is swap the first entry and the second. So Sn acts by permuting the vectors. We can also put in an action of un. And what un will do, if I take some element of un and I act on the same vector, all it will do is it will act with the same matrix U in every single slot. Now, what you can see is the first action is swapping vectors. It doesn't mix the entries around, it just swaps the different vectors around in the product. The second action shuffles the entries inside each vector, but it shuffles in exactly the same way in every single slot. So it's quite obvious that if we swap them and then shuffled, we'll get exactly the same answer as if we shuffled and then swapped.
But should that have been U E1 E2 plus E1 U E2?
No, UE1 tensor, UE2 tensor.
This is the group, not the gear.
Yeah, this is the group. UN, yep.
So it's on everything.
Yep.
So if you do U equal to 1 plus IH, then you get the...
You'll get the usual co-product, yeah, for the Lie algebra. So the point is, it's quite easy to see now these two actions commute. So these two define commuting actions. And so because of that, you can diagonalize them simultaneously. And one nice thing about this space is the following. I will just illustrate it for n is equal to 3. So for n is equal to 3, so what, okay, I want to make a claim that I will just illustrate for n is equal to 3. And the claim is, after diagonalizing action of un and Sn, every state is uniquely labeled as, so we'll have some Young diagram R. R has got n boxes, no more than n rows. We then have an index, let me call this little I, and this runs over states in Sn irrep R. So I can think about some symmetric group representation labeled by R, but I can also think about a UN representation labeled by R. There's I, and this runs over UN representation R. So you pick a Young diagram. That labels both a representation of the symmetric group and the unitary group. And it turns out that after you've picked R, if you pick some state from the symmetric group representation and some state from the unitary group representation, you have labeled all of the states inside the space.
But the boxes was the number of z's, which
Yes.
was not n.
That's right.
So the Young tableau is a Young tableau with, oh yes, so
N boxes, yep,
n boxes, but that's what also labels.
Yep.
Because of the cutoff.
exactly, yep.
No, but you could have small n greater than n, right? In that sense, in the Young diagram will have many boxes.
But that's also
That's-
a legal
yep.
Young diagram for SUN, as long as
Yep.
it doesn't have more than n u's. So the cutoff is always something.
Yep.
That's exactly what it's like.
Okay. Okay, so I just want to give you a simple example.
So another stupid question.
Sure.
So far we are counting the gauge invariants, right? The UN invariants.
Yep.
So what does it mean that we are counting representations of UN? That thing correspond also to the real representation of the UN.
Okay, so for each representation of Sn, you have a gauge invariant operator. But now what I'm showing you inside this space, the representations of Sn and Un are married together. They're married together because these two actions commute on where z tends to n naturally acts. So I could also say for each representation of Un, I have a gauge invariant operator.
In this part, you're not counting gauge invariants. You're just taking the space state, this
Yeah.
state space, which carries UN.
Yes.
So for this theorem, you're not worried about gauge
Yeah.
invariants.
But finally, the counting
How
is
it will
also
be
in
used.
terms of
Un, yeah. Are you asking if it's gauge invariant, why would a representation of Un play a role?
Yeah.
Okay, so one way to understand it is as follows. If we take Z tensor n, we have n row indices, n column indices. I can put the row indices into a representation of Un and the column indices into a representation of Un. Then to get the gauge invariant, I would like to take the tensor product of these two and extract the singlet. So
I said this one is telling you which one is clicking with which.
exactly, yep.
So is it not that this relation of taking a class function and writing this as a sum? Is it if
I
you
request this when you use the words like class function, explain to us more, please.
a function?
Things defined up to conjugacy.
Yes.
Please say that.
Is it not the generalization of Frobenius relations for, let's say, a group SUN? Is it not that if you have a representation R of SUN, you want to write down character of an element in this representation, and then you can this decomposition, is it not exactly the Frobenius decomposition?
Yes, it is. Yep. So now, so that's so you're talking about this character formula for writing UN characters?
I'm looking at the relation from the opposite way. Like you had a function which was defined on conjugacy class, and you motivated this transformation as a Fourier transformation. And then for you it was sort of surprising that why the final representation was a representation of SUN. For example, where R is having maximum in number of rows.
Mm.
So if I look at it from the other direction, I am giving you a representation R of SUN,
Yep.
and I am asking for a character in this representation of
Yes.
an element.
Yes.
Then that can be expanded in using the same formula.
Very good.
And then that will be a Frobenius relation.
Absolutely, absolutely. So why am I presenting it to you like this? Later on, we'll build some gauge invariant operators. We'll see there's some different symmetry. For example, sometimes we'll get double cosets appearing. We'll want to do a Fourier transform to the double coset. In that case, I don't know what the Frobenius result is, but I can mimic what I did here, and I can learn what's going on. So this is always going to be the structure that I'll use to approach the problem. So always enumerate, find the redundancies, do some Fourier transform. Yeah, that's going to be the pattern. Good. Okay.
So
Yep.
sorry. So this also tells there's some counting check for the statement, right?
Good. So I want to do an example of that. Yep. Okay. So I mean, I really don't have a good feel by how much of the symmetric group is common knowledge. Is everybody happy with calculating dimensions of representations of the symmetric group?
You know, if you can do it in 5 minutes, my
Okay,
I mean,
good.
For the
Absolutely.
ignorant half of
Okay.
the audience.
Okay, so here is an example. So let's imagine that we have this representation of S6. There's 6 boxes, so we're talking about S6. Yes.
In the above line, it's I is only runs over states in
UN.
representation of SSSN.
So okay, good. Sorry, I always use a little I and a big I. So this is bad notation, I guess. Do you mean little I?
Yeah.
This is for SN, and that's for UN. Yeah. So for S6, it's S6 because you've got 6 boxes. You might want to know what is the dimension of this representation. Whenever I write dimension of this representation, I will write D, and I'll put R sitting over there. But it's a little d. And then what this is given by, it's n factorial. So here we would have 6 factorial. And then we would divide by what's called the hooks. So hooks for this Young diagram. Now what are the hooks? Each box has a hook associated with it. Draw a line coming from the bottom of the Young diagram going out the edge, and the elbow of the line is in the box, which number you're considering. So now we go through 1, 2, 3, 4, 5. So that hook length would be 5. Okay? What would this hook length be? 3. So what this dimension will be, it will be 6 factorial over 5 times 3 times 3 times 1 times 1, which would be 16. So this, as a symmetric group rep, would have a dimension of 16. The other thing that we will want to do is calculate dimensions of these things as unitary group representations. And in that case, so for UN, same Young diagram. Let me draw it a little bit bigger. But now the dimension formula is slightly different. So we've got something called the factors over the hooks. So the hooks is exactly the same quantity we've just calculated. For the factors, you start by putting an n into the first box, and every time you go this way, you add 1. And every time you go that way, you subtract 1. And then the dimension of this representation is given by the product of those numbers. Over the product of the hooks. So these are the 2 dimensions that we're going to be using. Okay? Now let's look at n is equal to 3.
And this is a formula for UN and not. Is there a difference between UN and SUN?
So what you would usually do, for example, when you multiply Young diagrams and things like that, in SUN you would cross out columns with n boxes. For UN you should just leave them there because they'll contribute to the U1. But apart from that, the counting, the dimensions and so on is exactly the same. Yeah.
Is there a value then for which agrees with the S?
Okay, I don't know, I've never checked that. You mean so that you can get a 16? I don't know. Yeah, I never.
There is no such.
In general, I think there's no relation, absolutely. Yeah. And the Young diagram means different things. So what this means for the representation is not completely clear. Later on, I'll show you how to read the representation of SN from the Young diagram. But in the UN story, it's the thing that you're familiar with. So you're probably used to symmetrizing in the rows and anti-symmetrizing in the columns. That story belongs to UN, not SN. SN is very different. Okay. So if we look...
Even
Yep.
thing is called the Weil dimension formula.
Yeah, you can get it from the Weil dimension formula, absolutely. Yep. So if we look at n is equal to 3, and you ask what is the dimension of V tensor 3, well, that's just n cubed, because we've taken a tensor product of 3 n-dimensional vector spaces. So now let's do the following.
I'll ask one more, sorry. Since you're doing this so beautifully and so simply, I'll ask one more thing, Mr. Sure. Suppose I write down a UN Young tableau.
Yep.
I want to translate this into a tensor of fundamentals.
Yes?
Then is the rule that the row symmetry properties are manifest, and that if you anti-symmetrize over columns, you get 0? Is that the rule? Do you know what I mean?
Okay. So I'm not sure how to do it. I know that there's these rules like symmetrizing by the row and then you anti-symmetrize on the column or something.
Now you can't do both
Yeah.
simultaneously.
So I'm going to show you I'm going to write down a formula which will give it to you.
Okay. Okay. Do you know if I said it right, Abhijit? So suppose, I'm sorry, you just
Yeah,
yes.
great.
Suppose I write down a tensor. I want to know what symmetry properties are manifest in my tensor. So is one way of saying it is that I write down a tensor such that the symmetries of rows are just manifest. That the tensor is symmetric under row interchanges. The antisymmetries of columns, it's not also antisymmetric in columns. You can't do something that is both. But the statement then is that if you take whatever you have and completely anti-symmetrize along columns, you'll get 0. Or sorry, completely symmetrize along columns.
Oh, symmetrize along columns. That will give you 0, absolutely. Yep. So let's look at n as 3. This has got a dimension of n cubed. And let's write down the Young diagram. So what possible Young diagrams are there? That's one. That's one. And that's one. Now let's look at dimensions of the symmetric group. So you guys know how to calculate these dimensions now. What would this dimension be?
3 factorial by 3, so that's
3 factorial by 3 factorial? 1. Here? 1. So those are the two warm-ups. Here's the tough one.
3 factorial by 2.
2, good, okay. So guys, sorry, Abhijit got it. Now, let's look at the dimension of the unitary group rep. And this is the same formula where you multiply the factors and divide by the hooks. So what you would get here is an n, and then you'd get n plus 1 times n plus 2. I'm going to write this as n squared plus 3n plus 2. And I need to divide by the hooks, which is 6. So I'm preparing the answer a little bit. Then for this one, we've got n into n squared minus 1 over 3. So let me put this over 6 and multiply by 2. And then for the last one, which is antisymmetric, it's n times n minus 1 times n minus 2. So it will be n squared minus 3n plus 2 over 6. And now let's multiply this by this, this by this, this by this, and add them together. Okay? So I'll have n squared plus 4n squared. Sorry, I'll have n cubed plus 4n cubed plus n cubed over 6, which is just n cubed. So I'll get an n cubed. Look at the n's. Here I have 3n minus 3n vanishes. Now look at the ones. There's a 2 minus 4 plus 2 vanishes. So the product of that dimension with that one plus that dimension with that one plus that dimension with that one is n cubed. But you can check it for V tensor n for any little n, and that's just checking that the dimensions really work for this. Okay? One natural thing that you might ask is how do we project onto a subspace of representation R? So now we've figured out what representations are inside this space. So how do we project onto a subspace of representation R?
So the really non-trivial thing is that the same representation here, that it's the same in the Sn and the U.
Absolutely. Yep. So you might wonder how general is this? There's actually a theorem called the double centralizer theorem, which says that if you have an algebra and you have the commutant, which is the biggest group of things that commute with that algebra, the representations will be labeled with the same labels. So this is actually a very general thing.
A little like spherical harmonics. You know, in SO4, spherical harmonics, so you've got spherical harmonics are representations of SU2 times SU2.
Yes.
But the spherical harmonics are those such that the two SU2 labels are the representations of
Are the same.
Yeah.
Right. Yeah, yeah.
LM M prime, that's what you mean.
Yeah.
Not LM L prime M prime.
Yeah, yeah.
But
Yeah.
LM M prime.
Yeah,
That's
exactly.
Okay, so let's build the projector onto representation R. And the formula for the projector always follows the same pattern. So here's the projector onto R. We will have 1 over n factorial. We'll have a sum over the group. We then have the character for sigma. And what we have sitting here, this is the sigma, this bunch of delta functions. Okay? The formula that we had before. So the delta I sigma 1, J1, and so on, delta I sigma n, Jn. So this thing will project us onto representation R. So some of the things you might like to check.
Wait, that's the action of the permutation. That's the action of the permutation element.
Exactly, on V tensor n. So the rule about symmetrizing rows and things like that, it's a simplification of this thing. Yeah. So this will do some symmetrization of indices and so on. Now, what kinds of things would you like to check? So these are things you can check. So first of all, this commutes with every element of the symmetric group. So that will be important. The other thing is, if you take a product of 2 of these guys.
And the sum is over elements of Sn or conjugacy classes of Sn?
Elements of Sn. Yeah. And a product of 2 of these projectors is proportional to delta Rs, so 0 if they're not the same, proportional to the projector. We will need this proportionality constant just now, so we'll talk about how to get it. And so it's a projector. And of course, if we take the sum over R of PR, you just get the identity. So all of the things that you would like for a set of projectors. If you now take a look at the Schur polynomial,
So this is a projector of the representation of R of UN or Sn?
both.
Since they're combined, it's the same.
Yeah.
If you're in a particular representation of Sn, you're in the same representation of Sn in this space.
So that was the formula that we had for the Schur polynomial. And if you take a look at what's going on, the 1 over n factorial matches, there's the same sum, there's the same character, and there's sigma. So in fact, the Schur polynomial is a trace of a projection operator onto Z tensor n. So now we have a good understanding of this redundancy, how it plays a role, what is the structure, and we're going to use this to get characters in a moment. One thing that I should say, so this is going to be important now, this guy is actually a character of UN.
Which you've just proved, right?
Absolutely, yep.
Because you projected onto that part
And
which was
traced.
the UN representation and
Exactly.
then taken the trace.
Exactly, yep. So
Sorry, what was chi R sigma? Did you discuss?
chi R sigma, this would be a character of the symmetric group. There are combinatorial algorithms to calculate it, things Murnaghan-Nakayama rule, I guess that's the one that people like the most. There are explicit recipes to write down the representation of the symmetric group and stuff like that. I haven't spoken too much about what these characters are, and in general, not completely trivial to get hold of them. But we know their orthogonality properties, and usually that's enough to do calculations. So the one formula that we will want to use is that we know chi R of the identity. That's just going to be the dimension of the UN representation R. And this is, of course, just the trace of PR, because there's just identity popping in. What we will do soon is calculate 2-point functions of Schur polynomials, and you'll see the only non-trivial part of the calculation is evaluating this trace, but we know it. So we'll be able to calculate these 2 functions quite explicitly. Okay, so that's the story of the Schur polynomial.
So this is the hard measure. This summation over sigma is the summation over the group, and chi r is the character. This is the action of the group. This is the hard measure you are projecting on this representation for this particular Sn group. Now, because of this theorem, Sn and UN are related, so you are projecting on the same representation of UN.
Yep.
This theorem is
So this is a way of proving that this is the character of the
that is the
other
theorem.
representation.
Yeah.
Once this theorem is proved, then you are using this theorem.
you use this theorem to prove that this is the character formula for U.
Yeah.
This is
Yeah. Okay, so that was the first example. And so now, if you like, we've got a nice list.
I missed that last line. Chi R, you were doing the
Oh,
chi.
so chi R
SUN, yeah?
of, right, so I'm plugging in an n by n identity matrix.
Yeah.
So I would expect to just get the dimension of the representation.
Yes.
And of course, if I plug the identity in here, I'm just getting the trace over the projector.
The projector, now this projector is thought of as an SUN projector or a SN projector?
SUN.
SUN projector.
Yeah. Okay.
Because you're using capital I, capital J.
Yes, that's correct.
Basically,
The multi-indices, exactly. Yep. Okay. So now, what I would like to do is calculate correlation functions of these Schur polynomials. So, in general, what would you do if you have zi of x1, z dagger kl of x2? So what is this two-point function? It would be delta il delta kj over 4 pi mod x1 minus x2 squared. The zz contraction would be 0, and the z dagger contraction would be 0. And what will you do? You'll take two operators, extract all possible pairs, replace each pair by this expression, and then sum over the i's, j's, k's, and l's. Okay? Now, what I want to do next is, I don't specifically want to consider the Wick contraction of that. I want to consider the Wick contraction of zi1, j1, all the way up to zin, jn, then z dagger, k1, l1, all the way up to z dagger, kn, ln. The other thing is, from now on, I'm just going to ignore the space dependence. I'm only interested in how the color indices contract. So I'm going to completely ignore that space dependence and only keep track of how the color indices are contracting. So imagine that I started off and I Wick contracted.
So the original Zs, were they gauge invariant?
No, so this is not gauge invariant, this guy's not gauge invariant.
No, sorry, but are you interested in some contraction of the original Z indices so that it was originally gauge invariant?
Eventually I will. So eventually I'm going to be using this particular contraction. But right now I'm just trying to work out for this non-gauge invariant operator, what is the Wick contractions.
Okay.
Now what would we get? We'd get something, so think about if we contract field 1, Z1 with Z dagger 1. So we would just get a delta I1, L1, delta K1, J1. Then I could contract 2 with 2, 3 with 3, go all the way up to N with N. And then there would be a second term. How many different Wick contractions would there be in total?
Yeah, depending on the permutation of the
Permutations. So how many permutations are there? N factorial. So we're talking about Sn. And every single one of these guys is some sigma ij. So what you can check quite nicely is that this thing is just a sum over sigmas inside Sn of sigma il sigma inverse kj. So that's now the full set of contractions. So now let's try to calculate a two-point function of two Schur polynomials. So we've got chi r of z.
And sigma inverse, because we contract one Z, you contract both these indices and those.
Exactly, yep. Chi r s dagger of z. And what is this equal to? Well, this first guy, this is PR, and we need to take a trace with sigma. So ij sigma j, sorry, z tensor n j I. Because the Schur is just a trace of p, with sigma.
P, I'm having trouble getting into my head. Could you write
Yep.
that P out as explicitly as
Sure.
possible?
Here it is.
Yeah. What are these ij indices?
What these ij indices are, so I stands for a multi-index. It's I sigma 1 up to I sigma of n, so to be a product of n Kronecker deltas, and the j's would run from j1 up to jn. And then for chi s, we would have ps, k al, z dagger tensor n al k, and again expected. Now, the only thing that we contract are these two guys, which gives this over here. So here we have sigma is an element of Sn. We have PR, Ij. Sigma, now we want Jk. PS, Kl, sigma inverse, what is it? Alj. Is it Li? Yes, thank you. Oh, have I got these? So JK, IL. Thank you. Yep, I. P commutes with sigma, so let's remember that. So this is a sum of sigmas, an element of Sn, trace of PR, sigma, PS, sigma inverse. Sigma commutes with PS, I can take it through. Sigma times sigma inverse is just the identity. The sum of the group will just give me n factorial. So in that step, I summed over all with contractions. So that's...
So sigma commits to this one because of the group Sn and
yes, exactly, because it's a projection operator. Yep. So in this step, we summed over all ribbon graphs. If little n was order n squared, you summed n squared factorial graphs using the projectors. Now, if you want to take a product of two projectors, PR, PS, this would be 1 over n factorial squared. We would have a sum over sigma and rho. We'd have a chi r for this rep of sigma, chi s for this guy, rho, and we would have sigma rho. To calculate this sum, let sigma rho be equal to psi, and then change to some new variables. Let's say we take sigma and psi, and what is psi equal to? Well, psi would just be equal to sigma rho. So everywhere where you see a sigma rho, replace it by psi. So this is going to be a psi. And everywhere where you see a rho, replace it by sigma inverse psi. So now you can see that there's a sigma appearing inside that character, a sigma inverse inside this character. Now you just use the fundamental orthogonality theorem for the group. Let me just remind you. So 1 over the order of the group, sum over the group. This is matrix representing element sigma and representation R, AB, gamma S, sigma inverse, CD. And this is equal to delta RS over the dimension of representation R multiplied by delta AD, delta BC. So this is just the fundamental orthogonality relation of the group, and this is almost the only identity that you need. Do that sum over sigma, and it's straightforward. There's a sigma appearing, there's a sigma appearing, and it's really completely straightforward. And the answer is that this gives you delta RS. It's that delta function, PR over dr. So that's the property that these projectors obey. So this formula over here is now n factorial delta RS over dr times by the trace of dr. But we know what the trace of PR is because we just calculate it from the character. So this is equal to n factorial delta rs over dr times by the dimension of the symmetric group representation R.
To get the projectors are orthogonal, did you need to use anything more than characters are orthogonal?
I just used the fundamental orthogonality relation of the group.
Equivalent to saying that the characters are orthogonal?
Yes, I think it is.
It's more.
Yeah.
More or same.
No, well, I think it's this. Oh,
I mean, I am saying that the characters that you use to construct the projector are orthogonal
okay.
under this
Yeah.
under this sum.
It's slightly more. I think it's slightly more because actually you have to. You're not. When you do the sum over sigma, at least from this derivation, when you do the sum over sigma, you're not just summing characters. You're actually summing group elements. And the reason for that is you had a product, something like chi r psi sigma, say, or maybe, maybe something like psi sigma, chi s sigma inverse. That's a character, but this isn't a character of sigma. I don't know if you can boil it down to characters somehow. I never tried,
Taking a trace.
but yeah, you are taking a trace over everything. It's just that that psi is sitting in there as well, and that can change the conjugacy class.
So what is the analog of this for compactly groups? For example, the above one will be projecting using R measure.
Yep.
In representation R. What is this identity that you used for?
The so it would be just the fundamental orthogonality relation. So for a compact group, so you would have an integral. So this would be with the Haar measure.
Yes.
So this would now be for some compact group. You will have gamma representation of the compact group, G, AB, gamma S, G inverse, CD.
And gamma is what?
So this would be the matrix representing group element G in representation R.
Okay.
This would be an integral over all of the G's. And this is delta Rs. And there's a delta function setting B equal to C, A equal to D. So that's the relation that I'm using, but for the finite group.
Sort of resolution of identity, resolution of delta function. Oh,
Yeah.
okay.
Okay.
Small dr is the dimension
Of the symmetric group. So in actual fact, if we now plug things in, this is n factorial, delta Rs. This little dr, this is our n factorial over Hooke's R rule. This dimension would be the product of the factors over the Hooke's R. And what you can see is Hooke's R cancels with Hooke's R. The n factorials cancel. And you'll end up getting Fr times by delta Rs. And this is just the product of the factors.
Oh, the SUN dimension formula also had to divide by Hooke's.
Yes.
Oh, I didn't get that. Okay.
Yeah. Okay. So now we've gotten correlators. And you can see that the Wick contractions also came naturally as permutations. So now we've got a nice basis for calculating things.
So this Fr is this n into n plus 1 into n plus 2 plus 1.
Exactly, exactly. So what I would like to ask now is, can we do an example with some physics? So I'd like to now study some correlation functions of operators with a dimension of order n squared.
So if your n, capital N was large and your representation was small,
Mhm.
then this is roughly n, capital N to the power number of boxes.
Exactly, yep, yep.
I mean, how would this be modified at 1 loop?
Okay, so in fact this doesn't get modified at one loop at all because this is the half BPS sector. So for this particular sector, whatever you're calculating in the free theory is exactly true and the full n is equal to 4. So this has been actually proved at the level of the correlation functions by, there was this paper by De Boer, Papadodimos and a few others. And they were showing that for extremal correlators, there are no corrections.
So
Okay. So I'll do an example probably.
What I'm asking is, in the space of representation, what is the notion of local Hamiltonian?
Okay.
In the long run?
So tomorrow I'll do an example where we have both z's and y's inside the operator. In that situation, the operator that you build in general is not BPS, and the dilatation operator has a non-trivial action. So you can act with the dilatation operator on these guys, and you can ask, what action does it have? And the answer is, at one loop, at most one box can move around on the Young diagram. At L loops, L boxes can move around. Yeah. So it's very much like the spin chain, where the spin was able to hop one side. Yeah.
So in this example that we'll do tomorrow, this is just by labeling the operators will be a bit more complicated because you have to keep track of which guy is Z and which guy is Y.
Exactly. Yep. Yep. And that'll actually, instead of doing a Fourier transform on the group, we'll do one on a double coset. Yeah. Okay. So so now I'd like to consider an example from physics, and it's the following. Let's study. So let's start off with something very simple. That's in the planar limit. So we have some operator On, and On is built out of some traces of z's. So, you know, I don't know, maybe some trace of z to the n1, trace of z to the n2, whatever. But if you sum over I, ni, this is order 1, meaning that as I scale n to infinity, I don't change the numbers n1, n2, and so on. And I'll consider some second operator, om, which is exactly the same, but I've got m1, m2, and so on. And again, the sum over I, mi, is order 1. If I wanted to calculate this two-point function, one thing that I could do, I could take On and I could expand it in a basis of Schur polynomials. Let me say alpha r of z, and I would sum over all representations r. One formula that I should have written down, so let me write it down now, is the following. So we had this, so this told you how to go from the traces to the Schurs. There's a formula that tells us how to go in the opposite direction, and it's very simple. And this follows just by using character orthogonality. So using something like this, you could very easily figure out some coefficients here, even if it was a sum of terms, and you would get something. And then over here, of course, this would be...
This formula I'm thinking of as giving a formula for the character in representation R in terms of polynomials of the character, or polynomials of the representation matrix in the fundamental representation.
Yes, that's right. Yep, absolutely. And I can think about OM as some sum, let's say, over S.
That was this first relation, this triad of C. That was this forbidden principle.
Exactly.
And the second one is resolution of identity used.
Right.
So there's OM, there's ON and OM. Now let's calculate this correlator. And we know what we will get. The two Schur polynomials will be orthogonal, and they'll give us a factor of FR. Oh, so this eventually boils down to FR. So we'll get...
The beta in which is dependent on S.
Very good, thank you. Another little test.
S and M.
Sorry? Well, that's true. Okay. Okay, so I'm not going to write the M, but it's true. So whatever operator we have inside the set, indeed. Okay, but I'm not going to put those, okay? Okay. And then FR. Okay? So that would be, that sum, that would give you the 2-point function. Now I want to do something different. Let's take the Schur polynomial, chi b, of z.
We are still in the free limit, right? We use this result.
Absolutely, we're going to use that result. Yep. We are doing things all in the free field theory, but thanks to these non-normalization theorems, we know we could compare to gravity if we want. Yeah. So I want to take chi b of z, and what b is going to be a Young diagram which has exactly n rows and m columns, and I'm going to take m to be order n, meaning that as I take n to infinity, I scale m with n. So m over n is fixed, some finite number. Okay? So this is an operator with order n squared fields in it. So delta for this guy would be order n squared.
So this is a rectangular diagram or any diagram?
Rectangular. So I'm looking specifically at the rectangular diagram. This corresponds to an LLM geometry. Okay, if you're not familiar with LLM geometries, what I'm going to say now won't make too much sense, but let me just say it. So this would correspond to an LLM geometry. And what happens with LLM geometries is you have to specify a boundary condition that tells you what it's a boundary condition for the supergravity equation. So a lot of the time when you want to think about the physics, you always think in terms of these boundary conditions. I'm going to tell you what this boundary condition is. The boundary condition is an annulus. The central white disk has got an area of m, and then you have this dark region, and so this is colored in annulus, and that's got an area of n. So there's some very definite supergravity background that is dual to this chi b of z. And what I would like to do, this correlation function over here, I could think of as being related to some sort of a gas of gravitons in AdS5 times S5. I now want to study the same gas of gravitons, but in this LLM geometry. So what is the correlator that I want to study?
So this M holds an N part place.
Yes?
So the holes are represented by the
Empty states?
horizontal things because they
Yeah.
are like dual giant gravitons.
Yes.
And the okay.
And as you change the shape of the diagram, this will.
Absolutely. In fact, horizontal edges give you radii of white regions. Vertical edges give you black regions. So the edge of the Young diagram would correspond to going through black and white regions on the LLM plane. So there's some detailed map between the two. So for example, if I had some perhaps Young diagram that looked like that, what the corresponding LLM geometry would look like is I would have a white disk set by that distance. I would then have a black annulus. The area of that would be set by that distance. I would then have a white ring by that distance, another black ring by that distance. So that would be the dual LLM geometry. For this thing, just an annulus. Maybe that's a bad annulus. And the correlator that I want to study is this. So I'm imagining that chi b and chi b dagger are inside here to create this big background. Now I'm going to take my operators representing these gravitons. So this will be ON, OM dagger. And I will normalize it by chi b dagger. And the question that I'd like to ask, so these are operators with a dimension of order n squared. The question I'd like to ask is, does this have a 1 over n expansion or not? And what does it look like? That's what we'd like to know.
I'm sorry, I missed.
Yep.
What is B and what is it?
Okay, so what's happening is we're considering these two operators.
Yes.
They both have order 1 fields in them.
Yes.
So this 2-point function would be telling you something about some gas of graviton, something like that, in AdS5 cross S5. It's a multi-particle state because there's multi-traces in each of those, and
So
you could
particular
calculate.
state in the gas of gravity.
Exactly.
Okay. And what is this? Chi?
Now what's happening is I'm taking chi b to represent some heavy operator. It is labeled, so it's a Schur polynomial, labeled by a Young diagram that has m columns and n rows, and I'm taking m to be order n. So this is going to be dual to some LLM geometry that corresponds to an annulus. So that's an operator of dimension order n squared. So now I'm interested in studying the dynamics of the same gas of gravitons, but in the LLM geometry.
So think of this as a 4-point function, or equivalently a 2-point function in the LLM vector.
Exactly, exactly. And what I would like to know is, does this have a nice 1 over n expansion?
Is this everything's Euclidean here?
Everything is Euclidean here, yes. Now,
If you want to create a state and another state, well, I suppose.
Yeah.
I was just wondering whether you wanted. I mean, in Lorentzian space, if you created a state, you had another final state. Maybe I mean you'd be putting this guy very early, this guy very late.
right,
And
and sticking these in the middle. I guess so. So here I'm just going to be focusing on the color contractions,
Okay.
but indeed I guess I should think of building the state very early in the past, then perturbing with this gas of gravitons, removing them, and then,
Okay.
yeah.
Robert, to let you know that in a few minutes the room will become unavailable.
Okay, great.
There's something
No problem. So I think in
at a natural
5-10 minutes, is that okay?
5 minutes.
Okay, 5 minutes, okay.
It
Now,
will technically become unavailable in 2 minutes, but
oh, I see, okay. So, well, what I could do is, I could pick up from this point next time.
if you think it's a natural point, it's
I think, so, within the next 5 minutes, this is as natural as any other. So I think this is, yes. Yes.